Ladies and gentlemen, let's continue with chapter 4 in the textbook of Cengel and Ghajar, Heat and Mass Transfer, the 5th edition, chapter 4. So chapter 4 is on transient heat transfer. Now what do we mean with transient? Transient means unsteady. It changes as a function of time. And sometimes it is easier to explain what steady is and what unsteady is before we get to transient. So let's just take a look at the difference between the two. Steady and unsteady. Steady is, if you look at any body, the same body, and we look at different points, measuring points inside the body, 1, 2, and 3, and N. There is point 1, there's point 2, there's point 3. So there's a number of points N. And we look typically at the behavior of the temperature as a function of time for both cases. Temperature as a function of time. So in this case, if we measure the temperature there or determine the temperature, then it will be like that. So it's not a function of time. It doesn't change as time goes on. So that might be the temperature at point 1. There will be the temperature at point 2, and maybe there's the temperature at point N. So the temperature is a function of time. In this case, for unsteady, let's suppose that is T equals 0. Then unsteady would be maybe this case where the temperature was steady, but at T equals 0, the temperature now becomes a function of time. And then maybe the same with point 2, like that, and that is the temperature, and there is the temperature N, and it varies as a function of time, something like that. So this is unsteady heat transfer or transient heat transfer, and that is steady heat transfer. So up to chapter 3 in the textbook of Cengel and Ghajar, you've looked only at steady heat transfer. So that is what this chapter is then all about. It is introducing changes of the temperature as function of time. Now the first paragraph is paragraph 4.1, which is on lumped system analysis. Okay. Now what does this word lumped mean? For those of you of which English is not your first language, lumped means it is combined, it is put together, it is an aggregate, an Afrikaans, klont, okay, is the Afrikaans word for that. And this is paragraph 4.1 of approximately, I think, about 10 paragraphs in this textbook. And in each one of them, another approach is followed of determining the temperature as a function of time. Okay? And we're going to do different geometries. And the challenge for many of you, or most of you in the test and exam, is I'm going to give you a problem. And I'm not going to tell you which method you should use. And students specifically have a big problem with this one, to distinguish when should they use the lump system approach. So the first of many answers I'm going to give to you is that this is almost the simplest method, the crudest one, and most probably the most inaccurate one. But in some cases, very select few cases, it gives excellent answers. But it is very important that you must be able to distinguish between the different methods in terms of when you should use it. So let's look at, I'm going to say, with this chapter, you can actually divide all the work of transient and unsteady heat transfer into two categories, a category 1 and a category 2. And the category 1 is the lump system approach. And the category 2 is all the others. Okay. Now, what is the difference between these two methods? Before I do the derivation of the equation, one of the most important differences is that if we consider any arbitrary body, and again, we want to look at how the temperature changes as a function of time for many different points. Just as an illustrative example, I'm giving 2 points. Okay. With a lump system approach, if that is equal to t equals 0, the solution is going to look like that. Okay. The solution is going to look like that, of temperature as a function of time. While with the others, it's going to give something like that. So what is the first major difference of the lump system approach? The lump system approach can almost not distinguish between the different temperatures in a body. They all have the same temperature, and therefore all of them have the same behavior, how the temperature changes as a function of time. While in this body, it is not the case. Okay? And we will do some examples in this regard. And let's start with the derivation of the equation that we can use for the lump system approach. And the derivation consists firstly of considering any arbitrary body with a certain mass m, with a certain volume. Okay. Take note, a special V, a fat V with a horizontal line through it, because in this course we will also use V for velocity. Okay. It will have a certain density of certain Cp value, and it will have a certain initial temperature, Ti. So Ti is the temperature at T equals 0. Ti is the temperature at T equals 0. And on the outside, here we've got the outside area is the surface area AS. And then we also have the outside temperature, T infinite, far away from the body. The heat transfer rate. And in this case, we are going to assume that this temperature is larger than that temperature. If not, then everything just works the other way around. And therefore, there's a heat transfer rate from the high temperature to the low temperature to the body. So, if we consider, firstly, the heat transfer rate. Heat transfer rate is the joules per second. Okay. It is like an empty can, and you put in a hose, and every second there's 1 kilograms per second of water going in. 1 kilograms per second, 1 kilograms per second. It's the heat transfer rate. So it is the joules per second. And the unit for that, of course, is watts. Okay. Now, this body was initially at a constant temperature, so it didn't get up any heat. Okay. So therefore, its heat transfer rate in the beginning would be equal to 0. And then the heat transfer rate, you should do something like, at T equals 0, something like that. So at T equals 0, this temperature difference is the largest. Okay, so let's suppose this is 100 degrees Celsius and that is 0. So at T equals 0, the temperature difference is 100. So lots of heat can go in. But as the heat goes in, this temperature will rise. to 99, etc. So the delta T becomes smaller and smaller and smaller. So therefore the heat transfer rate would be very large in the beginning, and it would then go lower and lower until actually, as a matter of fact, it goes to 0. Okay. Now let's suppose this is delta T, and that would obviously be T equals 0. So after a certain delta T, average heat transfer rate would be approximately that. You agree? So you just integrate this and you divide by delta T, and that will give you the average heat transfer rate during a delta T. Now the joules, the heat is measured in joules that the body receives. Okay. So let's suppose you had a can, okay, and here the water will flow in at T equals 0. Now a body would normally have some heat already in it. Why? Because its temperature is not 0 Kelvin. So normally we as mechanical engineers do not work with bodies like that. Okay? So therefore it is almost like water in a container. Okay? And T equals 0, the water will go in. And with time, obviously the water will become more and more, and the liters or the kilograms will increase. And that is the same as the heat. So at T equals 0, it will have something. Okay, so that is equal actually T equals 0. Again, that is like that. So the additional heat that is being added would be that part. Again, in a time period delta T. Is that clear to you? So heat transfer rate is like the water flowing in at 2 kilograms per second. Okay. The heat is like the mass, which at T equals 0 was maybe there were 100 kilograms of water in the can, and now 3 minutes later it is 120 kilograms. Okay. It increases as you put it in. Do you understand that? Okay. Now, using that concept, we can then say that the heat transfer rate into the body, is equal to Q divided by delta T. The heat transfer rate is like the mass flow rate. How much kilograms that you put in over a certain period, which is 3 minutes. It's the heat transfer rate. And in this case, it will be 20 kilograms per second. Okay. Right, so now if we look at the heat transfer rate into the body, the heat transfer rate into the body was by convection heat transfer. And you've done in chapter 1, you've done the 3 different types of heat transfer. It was conduction heat transfer, it was convection heat transfer, and radiation heat transfer. So with the heat transfer rate going in is the heat transfer coefficient multiplied by the surface area multiplied by the temperature, which is T infinite, minus the temperature of the body. But it changes as a function of time. So at T equals 0, this body, let's suppose, was at 0, and that temperature was 100. Okay. Now let's suppose 1 second later this temperature increased to 1 and that temperature to 100. Okay. So you can see that the delta T was originally 100 and now the delta T is 99. So the temperature of the body, this is the temperature I'm referring to. So it's T infinite minus the temperature of the body. Okay. And with a lumped system approach, we say that all the temperatures inside the body is the same. Okay. So that is the convection heat transfer rate going into the body is equal to Q. And what is our Q equal to? It is mCp dt from our thermodynamics. mCp dt, how much heat is inside the body, divided by, now we get more fancy and we say it is dt, not delta T, because we want to solve this thing mathematically. Take into consideration that the mass we can actually write as the density multiplied by the volume of the body. And a mathematical trick that you've used many times is dt we can write as d t minus t infinite. Why? Because this is a constant. And if I do the differentiation, then that one is just going to disappear in any case. So if we take that and we substitute it in here, that mass goes in there. This dt goes into there. Then we can write this equation as the heat transfer coefficient multiplied by the surface area, T infinite minus the temperature of the body at any specific time period T is equal to rho multiplied by the volume multiplied by Cp multiplied by d, T minus T infinite divided by dt. Are you happy with that? Right. So maybe you can see where we're going with this, and you can see that here we've got a d temperature and there a dt. So we would like to integrate it, so we're going to move the two terms separate. So let's put the temperature terms to the left. And that is then equal to d, T minus T infinite, divided by T infinite minus the temperature as function of T is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume Cp and dt. Is that right? I've specifically put in this step in the textbook because you'll see in the textbook there's a minus sign and students always can't figure out now where does this minus sign come from. But it's very easy. It is just in terms of this temperature. So if we write this as T minus T infinite, we have to put in the minus sign. And that is what we're going to do now. So we can write this equation as d T minus T infinite divided by the temperature as function of time minus T infinite is equal to minus h, the surface area divided by rho, the volume Cp multiplied by dt. And you should recognize it now as actually an equation typically like dt divided by dt is equal to c dt. You see that? Obviously, we make now the assumption that that is a constant. So the density, the volume, and the Cp value do not change as a function of time. It's not an exact constant because the Cp is actually a function of temperature. Okay? But for small temperature differences, it's a brilliant assumption. No problem with it. Right. So if we now go through the linear, through the integration, we get the ln of the temperature as a function of T minus T infinite, like that, is then equal to minus B T, okay, where B is equal to the transfer coefficient, surface area, divided by rho, the volume, and Cp. It's just the constant. In the integration, when T is equal to 0, then this temperature is equal to Ti. You agree? So that temperature is Ti, T equals 0. Then what we want to solve is we want to get the temperature T as a function of time. So there are all our boundary conditions. We can solve it and we can make it neat. I'm not going to bore you with that. It's very easy. So the temperature difference, going to write it as that, is equal to E to the minus BT. And that is now the final equation for us, for the lumped system approach. Take note of the temperature, which has now been written in a non-dimensional format. And we are going to do it a lot in this module. Write the temperatures in a non-dimensional format. In terms of the solution, if we now go and look at the solution of temperature as a function of time, and if that is equal to Ti, the initial temperature, and if that is equal to T infinite, then everything should happen between those two temperatures. You agree? Okay. So at T equals 0, the temperature is equal to that, and then you're going to get a solution for that with a specific value of B1 specifically looking like that. And if B2 becomes larger, then the solution would do that. That is B2, and then B3. So in general, as B increases, we'll get that type of result. Obviously, I've shown the results or the graph now where T infinite is larger than Ti. If it's the other way around, then we will get solutions like that, just the opposite. Okay. So that is the theoretical derivation for the lumped system method. Any questions on that, ladies and gentlemen? Nothing? Okay. Let's do an example. Okay. And the example will be a sphere. There is the sphere. It's not to scale because its diameter is 10 millimeters. Small ball bearing. Okay. And the initial temperature of this ball bearing is 200 degrees Celsius. And it's 200 all over, everywhere. It's made from silver, so you can go and look in the tables. The K value for it is equal to 429 watts per meter Kelvin. And the density is 10,500 kilograms per cubic meters. And the Cp value is equal to 0.235 kilojoules per kilogram Kelvin. Now, a question that I get a lot from students after the first 2, 3, or 4 weeks is that some of these units, for example, Cp is in Kelvin, K is in Kelvin, heat transfer coefficient can be in Kelvin, but sometimes it is in Celsius. Okay. They're all the same, so you can change them around. Okay. And the reason is that normally we work in temperature differences. The Cp is relative to a certain value, so any delta T is going to give you the same answer. The only place where you cannot do it is in radiation heat transfer, where you have to work in kelvins. But for the rest, it doesn't matter. Okay. Right, so there's the ball bearing, and the ball bearing at t equals 0 is exposed to an environment where the temperature is 20 degrees Celsius. The heat transfer coefficient is equal to 10 watts per square meter degrees Celsius or Kelvin, it doesn't matter. And we would like to know how long will it take for the ball bearing to get to 40 degrees Celsius. So this temperature, how long will it take to get to 40? Do you all understand the problem? Right. So if we look at typically the B value, if we look at this equation, we can go and do some calculations before we put it into the equation. For example, we can see that we have to calculate the surface area and the volume. So I'm going to start with that. So the surface area of a sphere is equal to pi d squared. Very simple equation in terms of diameter, pi d squared. So therefore it is equal to pi multiplied by the diameter is 10. And the result is equal to 3.142 multiplied by the 10 to the minus 4 square meters. The volume of a sphere is equal to pi divided by 6 multiplied by d to the third. It's very elementary. I'm not going to do the substitution for you. You can go and do it yourself. But the result works out as 5.236 multiplied by 10 to the minus 7 cubic meters. Okay, the B value for the constant is equal to the heat transfer coefficient multiplied by the surface area divided by the density, the volume, and Cp. The heat transfer coefficient is 10. The surface area is up there, so I'm not going to put it in. You can do that yourself. The density is what, 10,500. The volume, there it is. And the Cp is equal to 0.235. You agree with that? You shouldn't agree with me. What's wrong? It's kilojoules, so be careful for that. In many of the tables, some cases it is kilo, mega, other cases not. So this should be 0.235 multiplied by 10 to the third. Okay. And the result is that B is equal to 0.002432, and its units is per second. So in terms of the formula that we've derived for the lump system, the temperature minus T infinite divided by the initial temperature minus T infinite is equal to E to the minus BT. The temperature, we want to know how long will it take before the temperature reaches 40 degrees Celsius. T infinite is 20. The initial temperature is 100 minus 20, okay, equal to E to the minus B minus 0.00243 multiplied by T. Is that right? Something wrong? Are you happy with it? Sorry? Oh yeah, sorry. Initial temperature is 200. Okay, right. Okay. Okay, something that you have to get used to is that in many cases there's quite a difference between what I write and what I mean and what I want to say. And with time, you will figure that out. Okay. Right, so T we can solve then as equal to 903.6 seconds, and that works out as 15 minutes. So it will take 15 minutes for the ball bearing temperature to decrease from 200 degrees Celsius to 40 degrees Celsius. Right. Now, what is really the crux of this problem that you need to understand? The crux of this problem is that for the heat transfer to occur from here to there, from the temperature of 200 to 200, is that there's a resistance against heat transfer. And you've done it in chapter 3. We consider that as a resistance element there, and there's another resistance element there. That is what causes the resistance against heat transfer. And the analogy is exactly the same as with electricity, the voltage difference, the current, and the resistance. The current and the heat transfer rate is the same. The voltage difference, the temperature difference is exactly the same. So, if we would now go and look, what is the resistance of that sphere in comparison with the resistance of convection heat transfer? I see we are running out of time, but you can go and calculate the resistance for a sphere is equal to 0.0371 per degree Celsius per watt. If you go and calculate that resistance. If you go and calculate the resistance for the convection heat transfer, it is 318.3 degrees C per watt. So what is really going on here? What is going on is that this ratio of the convection resistance divided by the resistance of the sphere is equal to 8,580. Okay. It therefore means that if you want to schematically give yourself an idea of what is going on here, and you would draw this distance of this resistance element as 1 millimeter, then that one is going to be 8.5 meters. So that is the ratio of the differences between the resistance elements. And that really is the secret in terms of the lumped body system. So in the lumped body system, this resistance is negligible in comparison with that resistance. And that is what you need to understand with the lumped system approach. But I will address that in the next lecture. Thank you very much. So, ladies and gentlemen, we've